We started off the chapter by learning how to balance redox reactions using the half reaction method, and now we're going to use redox reactions in various ways. One way they can be used is to generate electrical current. So what is electrical current? It's the flow of electric charge. And here we're talking about the flow of electrons moving through a wire, or we can have charge in the form of ions moving through a solution. So redox reactions can generate electrical current. Let's look at this example. We've got zinc metal and copper ions, and they're going to undergo a reaction to form zinc ions and copper metal. And that happens because electrons are transferred from the zinc to the copper ion. Zinc has a greater tendency to lose electrons, and so the zinc will transfer 2 electrons to a copper ion. Then the zinc atom becomes a zinc ion, which can dissolve in the aqueous solution, and the copper gets deposited on the zinc as solid copper. And that's going to look like this. So here we have a beaker of copper 2 sulfate solution, which has this characteristic blue color, and we have a zinc strip just sitting in there. And without doing anything to this, if you wait, you'll see black stuff, fuzzy stuff, growing on this strip of metal, and you'll see the blue color of the solution slowly going away. And what's happening here is that the zinc atoms in that strip of metal are giving 2 electrons to the copper ions. The copper ions then become copper atoms, which are not soluble, and so they're going to stick to the metal, which is where they became an atom. And the zinc atom that gave up its electrons is going to become an ion and float away. Any questions? Makes sense? So if we just do this in a beaker, it's interesting to watch, but we don't get anything productive out of it. If we separate the zinc atoms and the copper ions, we can force the electron transfer to occur through a wire. Then we have electrons moving through a wire, which is electrical current. And as we know, electrical current can be used to do all sorts of wonderful things. So this is called an electrochemical cell. It's a device in which a chemical reaction either produces or is carried out by an electrical current. So there are 2 types of electrochemical cells. A voltaic cell, also known as a galvanic cell, is where electrical current is produced. You have a spontaneous chemical reaction, and it produces electrical current. An electrolytic cell is where we can take a non-spontaneous chemical reaction and force it to happen by driving electrical current through it. Okay? So here's an illustration of a voltaic cell. So we've got our beakers with strips of metal in them. So here's a beaker. This has zinc nitrate solution and a zinc electrode here, solid piece of zinc. Over here we have another beaker that has copper nitrate in it and a solid piece of copper. Now, if these just sit here, nothing's going to happen. But remember, the zinc was pretty eager to give electrons to the copper ions. Well, there's no copper ions here, but it can send electrons through the wire to the copper electrode, and then it can give electrons to the copper ions, which then are going to deposit on the electrode. So each of these beakers is known as a half cell, and the reaction that occurs there is the half reaction. So here we have an oxidation half reaction. Zinc is forming zinc ions and 2 electrons. Those 2 electrons are being forced to travel through this wire, and then we have the reduction reaction where the copper 2 ions are getting the 2 electrons and becoming solid copper. This is going to work because when we look at these equilibria here, each metal in equilibrium with its ion. The zinc equilibrium lies further to the right, and so the zinc is going to tend to become zinc ion, and the copper ions will tend to become copper solid. Any questions yet? We use electricity all the time, but most of us really do not understand it. And even if you studied it a little bit, it's still a bit hard to understand. So we can think of electrical current as being analogous to flowing water. We all have experience with flowing water. We've played with water, it's kind of fun. We've seen rivers, and we know what water does, right? So the rate of electrons flowing through this wire is analogous to the rate of water flowing or moving. And we have a unit to measure that. It's called an ampere, abbreviated capital A. It's also often referred to as an amp, right? That's just a unit of electrical current. Another unit is Coulomb, capital C, not to be confused with degrees Celsius. And this is a unit of electrical charge. So mostly in chemistry, we talk about electrons being -1 and protons being +1. And those are useful in chemistry, but they're not so useful outside of chemistry. So a Coulomb is a unit of electrical charge that is equivalent to 6.242 times 10 to the 18th electrons. So an amp, 1 amp is 1 Coulomb per second. You do not need to remember that number. So we know that water movement or water current is driven by a difference in gravitational potential energy. What's the difference between a lake and a river? In a lake, the water's just sitting there, right? I mean, the wind might blow it, you can splash in it and stuff, but it's not moving from one side to the other. In a river, the water is moving from one place to another, and there is a current. Why does it move? Because of difference in potential energy. Because the head of the river, where it begins, is higher in elevation than it is later on. And so water is literally flowing downhill. Okay? So electrical current, being a lot like water, is also driven by a potential difference. It's not a gravitational potential difference. This potential difference is measured in joules per Coulomb. So the volt is the unit of potential difference. 1 volt is 1 joule per Coulomb. So if we have a large potential difference, then we've got a large difference in charge between the two electrodes, and we have a really strong tendency for electrons to flow. That's going to be like a steeply descending stream bed. So if you have water flowing down the side of a mountain, right, it's really steep and it's going to flow very fast. It's going to be hard to stop, right? Whereas, by the time the Kings River gets down to like Reedley, it's almost level, and so it's not flowing very fast anymore. Electromotive force, or EMF, is another word, another term used for potential difference. It's the force that results in the motion of electrons. Any questions yet? So the cell potential, which is like the difference in elevation between the beginning and the ending of a stream, it's the difference in potential energy between where the electrons came from and where they're going, also known as cell EMF. potential difference between two electrodes in that voltaic cell. And that cell potential is going to depend on the relative tendencies of the reactants to undergo either oxidation or reduction. If we have a high positive cell potential, this happens when we have a substance with a high tendency toward oxidation being paired with a substance with a high tendency toward reduction. So we've got one half reaction that really likes to go in the direction of reduction, and we have another half reaction that prefers to go in the direction of oxidation. And these guys cooperate really well, and so we get big electron transfer. That cell potential is also going to depend on the concentrations in the cells and the temperature, and we'll talk more about those later. So E cell is the cell potential. Standard cell potential is E cell with that degree symbol. So when we put that little 0 or degree symbol up there, that means standard. That means things are going to be in their standard conditions. And here, standard conditions are very much like the other standard states we've talked about. Concentrations of 1 mole per liter for solutions, or pressures of 1 atmosphere. Okay, which statement best captures the difference between volt and amps? It's fine to look back at the previous slides. So the volt quantifies difference in potential energy. The amp quantifies flow of electrical current. Choice B is the opposite. Amp is the difference in electrical potential energy. Volt is the flow of electrical current. Or choice C, there are two different units used to measure the same thing. They both measure flow of electrical current. A. Yeah, the answer is A. And, that's not something that I would choose as a great exam question, but it's important to talk about because volts and amps are both associated with electricity, but they are not at all the same thing. They measure very different things. So I suppose if we go back to the stream analogy, the volt would be like the elevation difference between the beginning of the stream and the end of the stream. Whereas amp would be the current or the flow, usually measured in cubic feet per second, of water. And oftentimes these are related to each other. If one's high, the other's high, but they are not measuring the same thing. So continuing with this voltaic cell with zinc and copper ions, the standard cell potential for this voltaic cell is plus 1.10 volts. And this is dependent on how likely zinc is to lose electrons and how likely copper is to gain electrons. If we, excuse me, if we replace the zinc with nickel instead, nickel has a lower tendency to be oxidized. And so then the cell potential here is going to be smaller. So this is like taking that stream and maybe now the top of the stream is at a lower elevation, right? So the difference in elevation is less, the difference in potential is less, 0.62 volts. If we have a negative cell potential, that means that the forward reaction is not spontaneous. It doesn't go in that direction. It'd be like water flowing uphill. It doesn't happen. Okay, here's some terms that we do need to get straight. And like so many things, we have pairs that we have to associate with each other. Oxidation, reduction, anode, cathode. How do we keep these straight? Well, here in the italics is what works for me. So we need to know, does oxidation occur at the anode or the cathode? Oxidation occurs at the anode, and I remember this because both of these start with vowels, O and A. Reduction occurs at the cathode, and if you shorten those words, you get red cat. So, if you switch them around, you'd get red Ann or ox cat. It's like, well, red cat makes more sense, right? So oxidation occurs at the anode, reduction occurs at the cathode. The anode is going to be more negatively charged, just like anions are negative. The cathode is more positively charged, like cations are positive, right? So the cathode's positive, the anode is negative. Electrons then are going to flow from the anode to the cathode. Electrons have a negative charge. Like charges repel. You've got electrons in the anode, negative and negative. They are repelled, they want to go away. And they have a path towards the cathode, which is positively charged. So the electrons are moving from the anode to the cathode. Okay? You might need to, practice that a little bit, make flashcards or something. So if we have electrons flowing from the anode to the cathode and nothing else going on, we get a buildup of charge in the solutions, right? The solution around the anode would become positive because it's lost all these electrons, and the solution at the cathode would become negative, and then the electrons aren't going to flow anymore. So we use a salt bridge to allow counterions to flow between those half cells without the solutions mixing. So remember we said that electrical current could be carried by electrons or by charged particles like ions. So this is often an inverted U-shaped tube. We used to call those U-tubes, but yeah, that means something else now. U-shaped tubes that have a strong electrolyte in them. Remember, electrolytes are soluble ionic compounds. Potassium nitrate is a real common one. And that's going to connect the two half cells. So this allows negative ions in the salt bridge to flow towards the anode to replace the electrons that left. And positive ions flow towards the cathode to neutralize the negative charge that is being created at the cathode. So this is that same picture. Here's our anode. Oxidation occurs at the anode. Oxidation is loss of electrons. So the zinc is losing electrons. The electrons are going through the wire. They're going through the light bulb and making it glow. And they're coming over here to the cathode, which has a positive charge. Here at the cathode, those two electrons are being given to a copper 2 ion, which then becomes a copper atom and sticks to the electrode. So we've moved an electron from this side to that side. In order to prevent a buildup of charge, we have to have something taking negative charge back, right? So this is the salt bridge, and it's got a semi-permeable plug here that allows ions to go through but doesn't allow mixing of the solutions. And so in here, the nitrate ions are going to go towards the anode because they are essentially replacing the electrons that left. This is getting all these electrons, and so the potassium ions are drawn to the right side. Over here, we've got zinc atoms losing 2 electrons, forming zinc ions in the solution. That's a positive charge, right? So the nitrate ions come over to balance out the positive charge of the zinc ions. Those electrons are flowing through the wire. And so we have electrical current flowing through the wire and back through the salt bridge. Any questions? So in a voltaic cell, in which direction do the electrons flow? From high potential energy to low potential energy, from the cathode to the anode, or from low potential energy to high potential energy? A would be a great guess, right? Because that's what things tend to do. They go from high energy to low energy, right? Things fall down, they don't fall up. So A is the correct answer. And we can illustrate it this way. So here we have two tanks, and they're connected so that water can flow from one to the other back and forth. Now, if these are connected, this is not how we would expect to find the water levels. We would expect them to be equal, right? Because nature wants to even everything out. Here we have water with high potential energy, and here we have low potential energy. So the water is going to flow from high potential energy to low potential energy. This is very much like a stream going down a mountain, except here we don't see, it's just a little different looking. Yeah. Mm-hmm. Mm-hmm.
There's left some negative ion in the beaker. The NO3 minus comes, and the negative goes in the...
Yeah, so what's happening here is that positive zinc ions are being created, right? And if you just are making positive ions, this whole solution is going to get a positive charge, right? And then why would electrons leave if this is positive? They're going to stay. They're not going to move anymore. Here, with the zinc ions being created here, the nitrate ions with a negative charge are going to move towards that. Essentially what's happening is that the nitrate ions are bringing electrons back to this side. Yeah. And so here we have copper ions, positive ions, being taken out of the solution, and there's nitrate ions here. So we're taking a bunch of copper ions out, we're left with a bunch of negative ions. So the potassium ions in the salt bridge come in and take the place of the copper ions that were taken out.
That does not neutralize the solution?
It doesn't neutralize the solution in terms of stopping the electric current, because potassium doesn't react with anything. If we don't allow this to flow, then there will be no flow of electrons through here. Because, you might have a couple of electrons go, and then they're like, okay, we've got a blockage here. We're building up charges that don't favor the movement of the electrons. And so if you're at all familiar with electrical circuits, in order for electricity to flow, you have to have a complete path for it to go. Because you don't have electrons like just being created somewhere, and then they're going somewhere else, and then what happens to them? It's always a flow of electrons. Here we don't see directly that the electrons are going from here through there, but that's essentially what the nitrate ions are doing. They are carrying negative charge from one side to the other. So a switch that turns off the on and off the lights, you could make a switch here by cutting this wire and just pulling it apart. It stops. And then if you put the ends back together, the light bulb comes on. You pull them apart, the light bulb goes off. It's a little fancier than that, but that's what a switch is. Any other questions? So, we've seen these pictures of electrochemical cells, and that's one way you can make an electrochemical cell, but of course, we don't have beakers of solutions in our cell phones, right? So we can represent electrochemical cells using something called a cell diagram or line notation. So this is the line notation used to represent that picture of the beakers. On one side, we have the species that are in the 1/2 reaction. We've got solid zinc and zinc ions. And on the other side, we have the species involved in the other half reaction. This double line in the middle represents the salt bridge. So these are separated from each other. And when we have different phases, different states of matter, solid and aqueous, those will be separated by a line. And over here we have different states, and so those are separated by a line. If we have two species on one side that are both aqueous, then they'd be separated by a comma instead. If you have all aqueous species here, the thing being oxidized and the thing being produced is also aqueous, then you need to use an inert electrode. You need something solid in there to hook your little clips onto, right? So we put an inert metal. Platinum is often used because it's very unreactive. So let's look at an example here. What we're doing here is kind of backwards of what we did last week in balancing equations. Here we have a balanced electrochemical equation, a balanced redox reaction, and we're going to pull it apart and look at the half reactions in it. This is the line notation for this cell. This is chemical equation describing what's happening in the cell. So, first we need to remember what's oxidation and what's reduction, right? Oxidation is loss of electrons. Reduction is gain of electrons. So let's look at these guys. The hydrogens and the water, those are usually just in there for charge and mass balance. So the things we're really looking at here is iron and manganese. So here, iron has no charge, and here it has a positive charge. Does that happen by gaining or losing electrons? Losing electrons. So the iron is losing electrons. Oxidation is loss of electrons. So the oxidation half reaction is Fe solid going to Fe 2 plus aqueous plus 2 electrons. You could copy down these coefficients if you want, but this would be the half reaction that you would start balancing this equation with. So that's this guy and this guy. Then the other one must be being reduced. So we've got permanganate ion becoming manganese ion. And there's electrons involved in that as well. Just looking at it like this, hard to see what the electrons are. So let's go ahead and bring back these coefficients here, because this is 5 iron is making 5 iron ions, and then we would get how many electrons from that? 10. This side is neutral, no charge. This side has positive 10, so this would be giving up 10 electrons. So down here, let's put the coefficients in. We had 2 and 2, and then we've got 16 hydrogens over there. This is not going to fit very well. 16 hydrogens. And then over here, we have 8 H2O liquid. This is reduction, so we must be gaining electrons. And if we look at the charges, over here we have +4. From this one, we have -2 and +16. So when we combine those, we get +14. And so how many electrons do we have to add over here to bring the 14 down to a 4? 10. So this is like taking it's the backwards of the half reaction method of balancing redox reactions. And we're not going to be doing this. I just want to show you how they are related to each other. Okay? Let's get rid of some of this. So the line notation for this cell, on the left is always the anode, and on the right is the cathode. And the way I remember that is A comes before C in the alphabet. So you put the first one on the left. So here's the anode, right? Oxidation occurs at the anode. So here we have iron, which is a solid, and then a line, and Fe2+, aqueous. So these are the two things in the oxidation half reaction. The double line here represents the salt bridge, and then we have the stuff involved in the reduction reaction at the cathode. And so we have MnO4-, that's aqueous. We have H+, aqueous. We have manganese ion, aqueous. Why do you suppose we left the water out? It's swimming in water, right? It's an aqueous solution. So, I mean, you could write it in there, but it's kind of silly. So that guy didn't make the cut. These are all aqueous. They're in solution. And so we have to have some solid there for this reaction to take place at, so that we can have the electron transfer. So here a strip of platinum is used as the electrode. Any questions? So here's an illustration of that. We have our anode over here, the solid iron, and that's going to be making iron 2+ ions. There are iron 2+ ions in this solution, and that produces electrons. Those electrons are going to leave, go through the light bulb, and come over here to this platinum electrode, which allows them to come down into the solution. And the manganese in the permanganate ion is getting reduced to Mn2+. We have a salt bridge here. Again, it's usually potassium nitrate just because it's a nice safe substance and it just doesn't react with anything. Potassium and nitrate don't precipitate with anything. So we don't have to worry about that. Any questions? So if everything in one of the half reactions is aqueous, then we need to put something solid in there to be the electrode. And so we're going to use something that's not going to get oxidized or reduced.